2.5b, we're looking at using the rational root theorem. So if a polynomial has integer coefficients, so integers are positive and negative whole numbers including 0, then every real solution of f of x equals 0 has the following form. So real solutions again are our x-intercepts, our roots. And so it has a form of p over q. And what p is factors of the constant, or the whole number, or the number at the back, and the factor of the leading coefficient. So for example, if we had a polynomial that was, let's say 3x cubed plus 7x squared minus 8, okay, minus 8. Then the factor of the constant is the number 8. The factor of the leading coefficient is our 3. And so P over Q, that works really well. But for me, I remember it better when I use B over F. B is the back, and then F is the front. Okay, because I have a hard time with P and Q, and maybe you don't, but this is how I refer to it, B over F. So I can remember that as like best friend, B over F. So let's do an example of that. Let's just do that 3x cubed plus 7x squared minus 8. And we want to write all the possible roots, all the possible solutions that we could have if this was our polynomial. And so it's back over front. And so if I have 8 over 3, what I want are factors of 8. Factors of 8 are 1 times 8, and then 2 times 4, and those are the factors of 8. The factors of 3 are 1 times 3. So when we're doing this, we have to use every possibility. So let's start with 1. Now what's going to happen is I'm going to name 1, and 1 has to be over the 1, and then 1 also has to be over the 3. And that's always plus or minus. So my first listing would be plus or minus 1 over the 1. The next one would be that same 1 over 3. Then let's do 2. So we're going to do the same thing, plus or minus 2 over the 1. And then plus or minus 2 over the 3. And then we keep on going with the rest of them until we list it all. So pause the video, see if you can try to name the rest of them for using 4 and 8. So the next one would be 4 over 1, and then plus or minus 4 over 3. Then we have plus or minus 8 over 1, and plus or minus 8 over 3. Now we don't have any duplicates in this case, right? It doesn't reduce in any way. Like if we had, for example, 8 over 4, which we don't, but if we had 8 over 4 is just 2, and notice we have a 2 already here. So we could always take it out if you have duplicates. Now one thing to note about this is that what these represent are all the possible solutions of this polynomial. So for example, if I'm looking at this, I would never try to divide the number 5 in here. So 5 is not a factor of 8 or 3, and so it kind of helps reduce the numbers that I have to try. Okay, so just to kind of, just thinking about that. Now, when do we use the rational root theorem? So here's an example where we have a polynomial and we want to find all the real solutions. And we have x cubed minus 8x squared plus 11x plus 20. Now, normally we try to factor this if possible. And so right now I have x cubed minus 8x squared. I could divide an x squared out of the front. But on the back, I can't think of anything that I could divide, right? The 11 is prime and, nothing goes into either of them. So I can't use factoring by grouping, so something that I'm used to using. So instead, what I'm going to use is a rational root theorem. And so I'm going to list all the possible solutions of this polynomial. Excuse me. And so it's going to be the back over the front. So back is that 20, that last number, over 1. So we're only really having to think about factors of 20. And so let's think about those. So I always go in order. I know 1, and then 1 times 20. Then 2 goes into 20. That's great. So 2, and then times 10. 2 times 10. Then 3 doesn't go into it, but 4 does. 4 times 5 is 20. And I know they're right next to each other because then I just go to 5 and 4. 5 times 4 is 20, so then I can stop. So these are all the possible values that could go into the above polynomial. So what I'm going to have to do at this point is I'm going to have to test. I'm going to test these solutions. Now, there isn't really like a shortcut to that. You just kind of have to try it out. I mean, we did shorten it already, right? Like we're never going to try 11, right? 11 is not a factor of 20. So we did reduce it. Now notice how many possibilities we have. We have 1 and -1, that's 2. So therefore 2, 4, 6, 8, 10, 12 possibilities. And so we're hoping that when we try one out, that'll work. So we can pick any of these numbers that we have, plus or minus 1, plus or minus 2, and so forth, and we're going to test using synthetic division. Now what we're trying to find when we do synthetic division is the remainder must equal 0. If the remainder equals 0, that means it is a factor. It's kind of like taking 7 divided by 63. And so we know that it's a factor. It goes in perfectly when we get a remainder of 0, for example. So like 9, 7 times 9 is 63. And notice we get a remainder of 0. So that is what we're trying to find when we are doing synthetic division. So we're just going to test. You're just going to pick numbers. I usually try like 1 and -1 first just because, I don't know, they're kind of nicer to multiply with. So let's do 1. Now remember when the 1 goes on the outside, that is really a factor of x minus 1. It's the opposite, right? So if x equals 1, then in factored form, it's x minus 1. It's opposite. Now with synthetic division, we write the coefficients of every term. So that's a 1, -8, 11, and 20. And then of course you write zeros for any missing terms. Now synthetic division, you bring down the first number. And then so 1 times 1 is 1, -8 plus 1 is -7. 1 times -7 is -7. 11 minus 7 is 4. 4 times 1 is 4, and this is 24. So this doesn't work, right? It doesn't go in, so we have to test another number. So let's go ahead and let's test -1. Okay, so just picking numbers. Like I could try 10 if I wanted to, right? It's just a matter of choice. So I'm going to go ahead and try -1. So that didn't work. So remember when it's -1, it's x plus 1 is our factor. I write that there so I don't forget that that is one of my factors. So that just reminds me to do that. So x plus 1, then we write the coefficients, 1, -8, 11, and 20. See if this works. So bring down the 1, the leading coefficient. 1 times -1 is -1. -8 minus 1 is -9. 1 times -9 is 9. 11 plus 9 is 20. And 20 times -1 is -20. And therefore we get a remainder of 0. And that's what we want. Now we look at what's left. 1, -9, and 20. And so let's write the x to the 0, x to the first, x squared. We're hoping that that is factorable. So let's write x plus 1. That was our factor. That worked. And then let's write the remainder of our synthetic division. So remember, if this is a remainder, this is the constant. This is x to the first and x squared. So this is x squared minus 9x plus 20, and that equals 0. So now let's see if we can factor this. And so you could use the x method or whatever you're most comfortable in factoring, and maybe you don't need that at all. So it's -4 times -5. -4 times -5 is 20. And -4 minus 5 is a -9. And so this factors to, so the x plus 1 still exists. And then it factors to x minus 4, x minus 5 equals 0. And so we use the rational root theorem in helping us to find one of the roots. And then we could factor it even further and solve it completely. So using zero product property, so it's just the opposite, right? You set each piece equal to 0. So you notice that x equals -1. And if you do the same thing here, x would equal a positive 4, and x will equal a 5. So that gave us all of our x-intercepts. And we could graph, right? So just kind of as a side note, you have your x-intercepts. Remember that the 20, the constant at the end, if you make x equal 0, then the y-intercept would be 0, 20. And you could graph, knowing what you know about leading coefficient, the degree of the polynomial, and so forth.